The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Wonderful. So now let's take a look at work done on a spring. In figure 6.5 here, we see we have, if we recall, even in our previous work lectures, when we had a force versus distance graph, right? The area under that graph would give us the work. Similarly, for a spring that obeys Hooke's law, right? When we have a force versus deformation graph as such, the area under the graph will give us the work done on a spring. And the area under the graph is, and because these two values are going to be, these two quantities here, they are proportional to one another, the area under the graph is always going to be a triangle as such. Now, if that's the case, if we recall, the area under a triangle, well, that's the area under the graph here, that is just a triangle, and the formula for the area of a triangle is just going to be 1/2 times base times height, right? And 1/2 times the base in our scenario here is just going to be the deformation, right, which is just x as such, and the height, as we see here, is just f. And what is the force equal to? Well, we know the force is going to be equal to the proportionality constant times its deformation, right? As such. Now, we can rewrite our equation as such, so we have 1/2 times k x squared, and that's what we have here as well, right? Okay, great. Now, that there was for the work done on a spring. Well, how about when we're dealing with a force, the restorative force for a spring? Well, then the work is just going to be negative, because if you recall, that force is just going to be equal in magnitude but opposite in direction. Thus, we end up with the following equation as such. Okay, great. Let's actually continue our discussion now on the next slide. Let me just get my pointer here. Wonderful. Elastic potential energy for a spring. Now let's begin here by reading our definition. Elastic potential energy is stored potential energy resulting from the deformation of an elastic object, for example, the stretch of a spring. If we recall, work was just the transfer of energy, right? So here we have the potential energy for a spring, right? Which is equal to the work done on the spring, which is 1/2 times x squared, which is just from our previous slide. Now, the potential energy for a spring when x equals 0, right? And x equals 0, that's when the spring is at equilibrium, is going to be 0. So the potential energy at this point is going to be 0. Now, anywhere along this elastic medium, when x is not at the 0 position, the potential energy is going to be a non-zero value. And whether the spring is being compressed or the spring is being stretched, we see that the potential energy increases and the potential energy also increases for a stretched or compressed spring. Okay,